All right, today we're diving into one of the absolute toughest problems in aerospace engineering. How do you accurately simulate vehicles flying at hypersonic speeds? The physics are just brutal, and the simulations have been a huge bottleneck. Well, until now. Let's get right into it.
Just imagine for a second you're designing a spacecraft that needs to re-enter the atmosphere, or maybe a hypersonic vehicle that's got to push Mach 15. At those kinds of speeds, the air around it stops behaving like a nice, simple fluid. It's more like a chaotic cloud of individual particles. Simulating that is unbelievably complex, and a single simulation run can take ages. And that slowness? It has become a massive roadblock for innovation.
Okay, so let's really get a clear picture of this problem. Why exactly are these simulations so painfully slow? Well, it all comes down to the really unique, kind of bizarre physics you find in these environments.
We're talking about a field called rarefied gas dynamics. This is the physics of a gas that's just so incredibly thin, think about the very edge of our atmosphere, that you can't get away with simple equations. You have to actually track individual molecules. The standard fluid dynamics equations that work perfectly for a 747, they completely break down here. You need something way more detailed, a simulation that works particle by particle. So for decades, the go-to tool for this job has been a method called Direct Simulation Monte Carlo, or DSMC for short. It's what everyone considers the gold standard. Why? Because it's super robust, it's incredibly accurate, and it gets the physics right by simulating millions of these little particles. But, and this is a big but, it has one huge, huge drawback. And here's a quote directly from the source material: "The computational burden of these tools has become a critical bottleneck." In plain English, what that means is that the most accurate tool we have is also the slowest. It's holding back innovation everywhere, from designing spacecraft to engineering tiny little micro devices. Okay, and this is where the story gets really interesting. A team of researchers looked at this speed problem and decided not to just build a slightly faster algorithm. No, they took a totally new approach. What if they could teach an AI to understand and predict the physics itself?
The best way to think about it is like this. If that super accurate but super slow DSMC simulation is the master craftsman, then the AI is its new apprentice. The AI's whole job is to just watch the master, learn exactly how it works, and then learn to produce the same incredible, high-quality results but in a tiny fraction of the time. This kind of model is called a surrogate model. So how exactly does this apprentice learn its craft? Well, first, you have the master do its thing. You run those slow, perfect simulations a few times to generate this pristine, high-quality data. That's your ground truth. Then, you feed all of that data to a neural network. And here is the absolute key, the thing that makes this so powerful. The AI isn't just memorizing the answers, not at all. It's learning the deep patterns, the fundamental physical rules that connect the inputs to the outputs. And once it's trained, it can make brand new, super accurate predictions almost instantly.
Now, what's so clever about this research is that they didn't just build one type of AI apprentice. Nope. They actually developed two totally distinct and really smart strategies to speed things up.
So the first path is what you could call an engine upgrade. They use a pretty standard deep neural network to find the single slowest part of the original simulation and just replace it with the AI. The second approach, it's way more ambitious. It's a full digital twin. For this, they used a different kind of AI called a neural operator, which is special because it's designed to learn the entire underlying physical equation. It's perfect for building a complete fast replica of the whole system from the ground up.
All right, so the theory sounds amazing, right? We've got our engine upgrade and our digital twin, but the big question is, does any of this actually work? Well, the researchers put these models through some seriously tough tests to find out.
First up, they put the engine upgrade to work on a classic fluid dynamics problem. And I mean, just look at this graph. The solid black lines, that's the ground truth from the old, slow simulation. And the dashed red lines, that's the AI's prediction. They are right on top of each other. It's a perfect match. The AI absolutely nailed.
And what about the speed? The team measured a 1.73 times speed up. Now, you might be thinking, that doesn't sound that fast. But here's the thing. Based on the laws of physics and computing, that is almost the perfect theoretical maximum speed up you could ever hope to get. It means the AI part is running so fast, its cost is basically zero. That bottleneck we talked about, it's just gone.
But here comes the real test for any AI model. Can it generalize? Can it predict something it has never ever been trained on? So the researchers decided to throw it a major curveball. They trained the AI on data up to 200 meters per second, and then they tested it on an extreme case at 800 meters per second. That's 4 times faster than anything it had ever seen before.
And the results is, honestly, it's just stunning. Take a look at these two plots. On the left, you've got speed, on the right, temperature. And again, the AI's prediction in red is a near-perfect overlay on the ground truth in black. Even in this crazy, extreme scenario that it was never trained for, the AI understood the physics so well that it made a flawless prediction. That is the sign of a truly robust and powerful AI.
All right, now for the main event. Let's circle all the way back to that hypersonic vehicle we started with. For this massive challenge, the researchers unleashed their digital twin approach to see if it could learn the incredibly complex physics of a Mach 15 flow over a cylinder.
So what are we looking at here? This first graph shows the Mach number, the speed. Those green dots are our ground truth from the slow, traditional simulation. And that solid orange line? That's the AI's prediction. And you can see it just perfectly captures that dramatic drop in speed as the flow smacks into the powerful shockwave in front of the object.
Next up, let's look at pressure. And again, same story. The AI in orange is beautifully tracking the ground truth, especially that huge spike in pressure right at the nose. But look closer. Do you see that faint orange shading around the line? That is super cool. Those are the model's uncertainty bands. It's the AI's way of telling us how confident it is. It's basically saying, hey, I'm really sure about this part, but things get a little chaotic and less certain right in the middle of that shockwave.
And finally, maybe the most critical piece of the puzzle for vehicle design, temperature. At Mach 15, the friction and compression get so intense that temperatures just skyrocket. And as you can see, the AI correctly predicts temperatures soaring past 10,000 Kelvin. To put that in perspective for you, that is hotter than the surface of the sun. This is the proof right here that the AI can handle the extreme physics you absolutely have to get right for designing safe re-entry vehicles.
So we've established it. The AI is fast and it's crazy accurate. But what does that really mean? What's the so what here for the engineers and scientists who actually work on these problems? What does this new speed truly unlock for them?
The impact of this is just profound. It fundamentally changes the entire design process. Instead of spending weeks to simulate just a handful of ideas, engineers can now test thousands of different designs in that same amount of time. They can optimize shapes, they can analyze safety margins, and they can start to explore truly radical new ideas that were always off limits simply because they were too expensive to even simulate. This is a complete game changer.
This work just brilliantly shows how AI can act as this powerful apprentice, learning from our very best, most accurate physical models to smash through these computational walls that have held us back for decades. We've seen it happen here in fluid dynamics. So the really interesting question is, what's next? Where's the next major scientific bottleneck that this kind of AI is going to shatter?